Okay, so we are kind of back. Before we go further, just a reminder, if you have any question online, don't hesitate to drop them in the chat. If I can answer them right now, I will, and if not, I will be happy to answer your question afterwards. Don't hesitate. So we saw that we could do a bunch of things. Again, let's go back to single wides. Okay, but of course, hopefully, we are not limited to only that. Okay, basically, the idea is to process multiple data. However, sometimes you may find this kind of small manipulation useful if you want to have a very small, even scalar operation on which you want to control the latency. I mean, if you want to do a fun exercise, you can actually write a scalar cosinus using Eve to vectorize the internal computation of the scalar polynomials. Same for shuffle. It lets you sometimes write a complex operation in a single, in a small bunch, sorry, of fast intrinsics. Yeah, what happens when we want to do more than that? Let's say I just want to, let's go back to this sample. I just want to, you know, let's add some stuff to the soup. I have a vector of stuff and I just want to apply a function on them. Okay, I want to process my data somehow. Let's clean that up. So, come on. So yeah, let's say you have a bunch of data like that. Let's do something in place. I mean, the scalar version of this is pretty much trivial. Okay, we'll just do something like that. So for every element of the vector, oops, sorry, I don't know, let's do something interesting. Let's do, I don't know, let's just do square root of E, something like this. So that's the classical scalar thing, okay? Not very much to go there. Is it auto-vectorized? That's an actual question. You should know by now. Well, Clegg is not very fond of auto-vectorizing it because the standard square root just do, you know, some Erno modifications. There is a global that is touched. Okay, so you could use fastmath to auto-vectorize that, but fastmath, I mean, the less you use it, the better you are, but that's my opinion. So we just got a loop and we got some square root on top of that. So what if I want to vectorize that? So I know that I can do vectorized operation using Eve-wide. I know that I need to go over every element of my array. So maybe what we should be doing is to say, okay, I will walk over my data from the first index to the last one. And instead of jumping one by one, I can just jump size of my register per size of my register. Let's try to write this manually. And we are going to see that at some point, we don't want to do this. So basically, what do we want to do? Let's simplify the problem right now, because there is one thing we need to be careful about. Let's say I work with floats on SSE2 or SSE4. I have 4 floats per register. Fine. What should I do if I have like 127 elements? I have some relicates, I have some extra value that doesn't fit into a full wide. So should I need to, like, you know, I need to compute how many elements they are and stop before the last wide and then do the last elements as a scalar or whatnot. That's a bit cumbersome. So let's simplify the task now and take the hypothesis that this vector size is a perfect multiple of whatever we have. Okay, let's simplify that. So what should I do? Well, I'm going to use index in this case. So we are starting from the beginning. I'm going to the end, and I have to jump by the size of my register. Oh, well, that's cool because this is something I have access to in a portable way. So I'm dealing with wide of floats, and I have a size element inside. Okay? So this will be 4 or 8 or 16 or whatever, depending on the type and depending on the architectures. But we are going to jump every size of the wire. So what I am going to do is that in, what should I do actually? I have to grab inside the wide a piece of my array, okay, right? So I have a wide offload then. Let's call it W. What I want to do is I want to load, okay, a piece of data from the vector. So you can use a constructor or you can use a load function. Load is a bit better because load can be masked. We are going to see that later. But we could use a constructor from a pointer. So what I am going to do is I am going to load from the address of x of I. Okay. So we take this address, load wide size element from there, okay, and put it into the correct register. Once I have that, I can actually call my square root on top of that. And now I need to put the data back. Because computing is cool, but storing the result is better. So we have a function for that, which is called store. And yeah, okay, I wrote the library, but I never remember. It's probably the vector first and then the address. If not, I will know, but normally it is this way. Is it? It is. Okay. And that's basically all I need to do. Load my data, so I have one single source, but you can do that for as many sources as you want. Do the vector computation using Eve functions that we conveniently name the same way as the scalar one most of the time, and we store the result back. You can see that we have a lot of functions and not much function member. This is because we want to keep the extensibility of the library as high as possible. It's always easier to add a function than to add a member function. So that's the scalar version that basically don't do much. What do we do there? Well, this is it. We load something in one of those CMD registers. We do the CMD version of the square root, and we store the result back. And we move by 4, because we have 4 things. So, I mean, it's not that complicated at this point, okay? Well, because we don't do much, but this is a thing. I load, I compute, I store. If you were there back in the 200s when Altivec was a thing, this has a name. That's what we call a blitter. Okay, we blit the data from one piece to another after doing the computation. That's a term that came from back in the day when we were writing graphics code by hand. Okay, and as we see there, okay, we got a pretty tight function already. Okay. That's fine. What happens if I change my target, right? So I should go by 8 now. So the scalar version didn't change much. Okay, we have this, am I positive or not? If yes, I do the thing. If not, I do the call. Okay. And then we do the same thing, except we go through the other registers, and we jump by a factor of 8 now because we double the number of elements inside our thing. Well, yeah, fine. But this is probably not efficient because square root has a very low latency in StreamD. We consume 1 register. There is like 15 other available. Okay? So what we probably should be doing is maybe we need to enroll to get more operation done per iterations. Okay. And the correct things to do is to think in terms of the following. Vectorization has a proper impact on performance when the data are either in the L1 or in the L2. Above that, the L2 to L3 cache miss cost will completely obliterate the performance. So normally we should be tight into the cache. Okay, let's say we have the perfect setup. Everybody is in the L1. Okay, the L1 cache bandwidth is basically 16 bytes per cycle, or more conveniently, 128 bits. Okay, so basically, if I can get that much things going on every cycle for every piece of register I do, I'm fine. The upper level of this means that we should have something around 64 bytes of data transiting in parallel from the L1. at most, something like that. 64 bytes, it's how many? Well, it's 4 registers of 16 bytes. That's 4 128 bits register at a time from the L1 to the L2. So what we want to do is probably unroll our things up to the fact that every iteration consumes 64 bytes. So we probably want to unroll by a factor of 4. Okay, yeah, I can do it by n, okay, by doing 4 times whatever, and then doing the epilogue from the remaining wide and so on and so forth. But you don't want to do that. Yeah, I don't know. We can do a raise of n, but I don't, and I'm not probably the only one who don't want to do that. We could probably play around with pragmas and whatnot to let the compiler unroll, but it doesn't want to do it right now, so, well, be it. So that's something also we want to do. So that's the trivial version, okay, right? If you look at what happens, you see that we are actually loading the data using this UPS version of the function call. That's an unaligned load. Okay, so we load the data without any respect of the alignment, so it works with any addresses ever. It's not the fastest way we can do that. You can force an aligned value, aligned load and an aligned store. Okay, but that means that you have some constraint on the way you allocate your data, so you know that you are aligned. Okay. We provide allocators for doing this. So if you want, you could have a vector of float with the Eve allocator, and we know that every data are aligned. But most of the time, it's not the big deal. The big deal is that you need to enroll, and you need to take care of the tail of the data as these remaining elements. Turns out that if we do this, let's change the scalar code there for a while. Let's say we do that, for example. That should be auto-vectorized. Or I will ask for a refund, but normally it's auto-vectorized. Yes, it is. And you see that Clang knows the drill, okay? Because it also did the unroll. So it knows that you can load 4 vectors at a time to maximize the cache hit. If you look at what it does the unrolling. It does 1, 2, 3 remaining vectors that may be there after the unrolling, and it finishes with the scalar remaining value, if any. Turns out you are not required to do that. There is another way to do this. And one thing we discovered while writing the library is that you can actually compute everything as registers. Because the hardware lets you load and store a bit after or a bit before the address of a SID register. So what we do in Eve, we are going to see it afterwards, is that we just load everything as if we had the size to do it. And the last or first element, we are going to mask the garbage value before doing the computation. So, well, we are halfway there, I would say, because we do the correct operation, we do the correct handling of the memory. What happens if I do the same code now? I mean, what happens if I do this? Do I get the correct thing? I hope so. Yeah. Okay. We still don't unroll because the compiler doesn't want to unroll our loop. It unrolls itself because it knows what it's doing. Okay. So we need to take unrolling into account. Sometimes unrolling will be a bad idea because your callable is, your function you call in the middle of your algorithm is very big. So you are not going to win a lot to replicate it. Either it's big in terms of code, it's a large function, or it's big in terms of register consumption. So if your function needs 4 registers to be computed, that means that you can only enroll by a factor of 2 at most, or something like that. So the same way we add opportunities, options on the regular function, maybe we should have option on how we want to generate algorithmic-like code. Okay. So you can do that by n. I could spend like 15 more minutes trying to get that to the level of the compiler, or pretty much so. But that will be a bit, inconvenient. So next to the building blocks for handling SIMD register and SIMD function, Eve provide, and I will be very clear about that, algorithms and building blocks for writing algorithms in a way that you don't have to take care about all these how many things do I need to repeat, what's the unrolling factor of that, and what not. We are going to have a look at that in a top-bottom way. We are going to look at the higher level algorithm first, see what we can do with that, and we are going to afterward see what we can write by hand using our building blocks. So what do I do there? I mean, let's go back to square root. The scalar version, okay, everybody is okay. That's what? That's a transform. That STD transform. So let's use the algorithm there. And if we want to write proper, contemporary, cool C++, we probably want to do something like this. Transform from X to X. Oh, wait. I said cool. Come on. Ranges, yeah. So from X to X, and we want to do the square root of the thing. Let me just space management. What do we say? Square root of E. So we probably want something like that, unless I forgot where the thing is going. Okay. What? Oh. Okay. That's okay. That's on me for not remembering how std range transform works. Oh, wait, no. That's for me to forget to compile with C++23 mostly. Okay. So is it that or not? Let me have a look at. Yeah, range. Okay, that should do it. Okay, it's not happy with that. Is GCC happy with that? No, it's not. Oh, come on. What did I forget? What did I forget? Oh, come on. Okay, where are you? Ranges transform thing. Oh, okay. Oh, sorry about that. Whatever. Is it that? Is it? Yeah. Okay. Took time to compile, so it's probably correct. Yeah. Let's have it this way. So we just call transform. Okay. On X, we store the result in X. Hopefully, the compiler is good enough to still auto-vectorize that. If not, again, we are going to ask for a refund. Well, it's not auto-vectorizing it because there is a square root, but it does the correct thing. So what I wish I could do is basically something like that. Well, good news, we can. So we have another module, which is called algo, that gives us algorithms. If algorithms have a range-based interface, so you pass the whole array instead of begin and end and whatnot, some of our API is slightly different from the standard one, but because the standard one is not correct, okay, for vectorization. But most of the time, it looks a lot like what you are going to write. So in this case, what we are going to do is to say, okay, I want to do this. So you can actually take that. Okay, let's keep this one for reference because it's interesting. Okay, let's make an algo one. So you can basically take this code, do this, and we are transforming in place. We are transforming x onto x. Okay, the result go to the same place where we are reading them. So there is some cases on some architectures where we can exploit this information. So we don't have transform. We have transform2 that takes an input and an output array and that basically transform. And we have a transform in place that basically do what it's written on the can, it's transform, and the results are written inside of whatever this thing is. Obviously, we cannot call std_sqrt there. We have to call Eve_sqrt. So now, let's have a look. Okay, compiles. So the joke is the following. If it compiles using Eve algorithm, it pretty much means that your algorithm has been vectorized. That's the deal we have with you. If you do sometimes some non-efficient or incorrect CMD patterns, you can sometimes detect them at compile time and you won't compile. Okay, but if you compile, well, it's pretty much okay. So that's the old case, okay. And now this is what we got. So this one is a bit bigger, okay. And if we look at what's going on, let me unzoom a bit. Sorry for the elders. Let's do something. Okay. We have 1, 2, 3, 4 square roots. So we get automatic unrolling, okay? And we have some support for the end of the things, okay? And we are done. And if we look at what we do, we never have any scalar-based operation. Everything's vectorized up to the end, okay? And we can see there that we have something going on. We have a masking thing going on. That's the so-called, I load some data with probably some garbage. I clean it up before calling it on the end, and I store them properly. So we wrote that, which is basically this. Okay, let's close this one. Which is basically that with a funny hat, okay? And it's vectorized. Use the correct implementation of the vectorizable function. Do the unrolling. Do the ending of the tail. Done. And if we look at what's going on, let's see, go back there. Yeah. We see that we also try to use a line load as much as possible. So what do? We also compute how much misalignment is there at the beginning of the array. We load a bit before that in an aligned fashion. We mask the beginning, compute that, we vectorize everything, and we vectorize the last trailing bits. And every element inside R is actually loaded in an aligned fashion. So you don't have to think about that. Now, sometimes it's not what you want to do because you have a big function or you don't really care about alignment and you want a more tight code, okay? So like the function, algorithms have options. So maybe you want to disable unrolling because unrolling is bad for your use case or your architecture is bad at unrolling or I don't know what. So you can pass off your option there. So let's just say that I don't want any unrolling. So stop the unrolling. Now, let's have a look. Where am I? Yeah. And in this case, yeah, we see that we are back to the very tight operation. Maybe you don't want to stop all unrolling. Maybe you want to change the unrolling. Maybe unrolling by 2 or by 16 is what you need. So we have this unroll options. Okay, again. And now we are unrolling by a factor of 2. Again, everything is simplified. You deal with the API of the function or the algorithm, and we do the correct thing. Now, let's have a look at something interesting. Okay, let's go back to this. And let's compile for IVX512. Okay, question for people online also, or in people in the room. Do you know why? Do you know the one issue AVX512 enabled hardware have? They have one issue. Adrien maybe knows about it. Anyone on the chat? If you don't know, stay like you are because it's cursed information. Sorry? Ah, yeah.
This is AVX512 we're talking about. It's bound to be cursed.
Yeah, it's bound to be cursed, but yeah. So the first generation of AVX512 enabled chips had a funny thing. Whenever you started running AVX512 instructions, well, it started, to eat the processor a bit too much, so the processor decided to don't clock themselves. Okay, because you are not going to do that.
If you are too old for your own good in the hardware, you will know that actually back in the day, AVX used to have the same problem.
Yeah.
When it was released.
It gets fixed properly. Okay?
Eventually.
Yeah, AVX had the same issue, but yeah. So AVX 512 chips don't clock themselves. But the problem with the first generation is that you don't clock the core that was doing the computation. So your chip was don't clocked. So you had your thread doing AVX 512 and 3 other threads on 3 other core doing normal stuff. Everybody get don't clocked. So that was cool because it was don't clocked exactly by a factor of 2, which is exactly the factor of 2 you win by vectorizing with AVX 512. Yeah, that's stupid, okay? Later on, they fix the thing, so only the core, which is doing AVX 512, is don't clocked. So the other cores that do normal things can still go at the same, as the correct, speed. So sometimes what you want to do with, the best thing you want to do with AVX 512 is not using it in the 512 mode, actually. And by the way, we know that because we went there. If you run Eve algorithm on an AVX 512 machine, well, you use AVX2 plus the AVX2 AVX 512 extension. So you can use the fast 256 bits operation that AVX 512 gives you, but we are not going to use AVX 512 register because most of the time you are going to get worse performance out of it, except when you do have some performance on that. So what we do is, in a conservative way, we don't allow use of AVX 512 implicitly in our algorithm. If you use wide, you get them. And you can write your own algorithm with wide, doing exactly what you want with AVX 512 register. That's our thing. But as soon as you use algorithm, we say, no, wait. You are going to get bad performances. It's not our fault. It's not your fault. So let's just, be cool about it. Now, if you want, you may actually ask for the full thing, even if, maybe you want to test. Maybe your algorithm is going to be fine. I don't know. So you can ask for removing what we call the frequency scaling. Okay. So we have an option for that. And actually, we have a YOL tutorial for that, if you want to know, because it's a bit of a doozy. And so we have this. We have this option, allow frequency scaling, that you can pass there. And then, okay, now you got ZMM registers coming up. And now, yeah, we do it using AVX 512. So maybe it will be good for you, maybe it won't. It's dependent on a lot of factors. So basically what we do is that we shield you from these bad bits. But if you want to have a look at and see if it's better if you use it, we have the, the clutch to remove it. A question we have quite frequently, without doing a joke on that, is why is this option so damn long to type? Allow frequency scaling. This is an advanced option. This is a complicated stuff. So if you give it complicated name, you know that if people wrote it consciously, they know what they want. Okay. Instead of having a small name or whatever that people can, put it by accident, there is no accident in typing Eve algo allow frequency scaling. Even if you, how to say that, you drop your keyboard and something fall on it randomly, you are not going to type that. So you have that. This is very x86 specific, but that's the best way we find out about not having people shooting themselves in the foot with this architecture. If you use that on any other architecture, it will work, but it won't do anything because we have no frequency scaling issue. Okay, so why? Fine. Okay, let's go back to sane thing. So that's transform in place. We have a bunch of other. A question in the room, maybe.
What is the risk of using this?
So if you use the risk of using the option or the other one? If you use that?
Yeah.
Okay, this will let the library use the full AVX 512 systems, okay, with the 512 bits registers. This means that maybe, depending on your hardware, because I don't know your hardware exactly, I just know that you have AVX 512, maybe you have an old hardware, and then you will get slowed down on your application for no reason, because I started doing that. And if you have a more recent one, you may not have the speed up you think you should have, because it will be slowed down. But sometimes some algorithm with some function, you will get a speed up. So what we do is that if you don't put it, you get the guaranteed proper 256 bits behavior, no issue of slowdown in the rest of your code, okay? And if you do this, you are basically saying that I know that my hardware can decide to slow down parts of my chip for no reasons, but I know what I do because I need those 512 instructions. So you may get slowdown in other part of your application, depending on the actual hardware you have.
Thanks.
Well, it gets better now, I guess. The latest one are less prone to this issue, and the slowdown is less than 2, so it's a bit better. But sometimes, if you don't control the hardware you have, which is sometimes, I mean, if you use some supercomputing center, you were not part of the process for deciding which chip was on the machine. You have to deal with that. And this is actually a way to say, okay, I know what I'm doing. Let me just test maybe. Okay, and if I'm okay with the bench, I will let it, and if I'm not okay, I can remove it. Okay. Again, it's a clutch, so you can decide if you are happy with the full-blown generation or not. There is, I mean, there is no impact on the correction of the computation or the memory consumption. It's just that you are at the mercy of the CPU deciding to go slower. That's all.
But it can be more energy efficient.
Yes, probably. I mean, it's all a trade-off game again.
Yeah.
So and again, as for every other trade-off, we have this philosophy of just having an option for that because we don't know, because there is a lot of external information we can't exploit at the compilation level. So we just give people some, leverage on that. Mm-hmm. And so what you can do, for example, is that you can have your algorithm written twice, one with and one with other. You bench the both, you see how it behaves, and you can make informed decision at the end.
Okay.
Okay.
Thanks.
No problem. Okay, let's go back to more same things. So as I say, we have different algorithms. So transform in place, transform to. We have reductions that are always vectorized, just saying. We have more complicated algorithms like find if, remove if, search, scan, stuff like that. Okay. Pretty much everything. The only one that eludes us right now is we still haven't an efficient store and partition. That's some work in progress, but it's really complicated to get that proper. So we can write stuff with that. But that's not the only thing we can do with algorithms, actually. If you look at what the STID range provides, you also have views. And there is one very interesting thing we can do is processing data as some sort of structure. Okay, so let's change a bit what we want to do there. I'm just not even hiding it now. Let's say you want to process some data that are basically a complex number in 2 arrays. Okay. So you have a bunch of real values, you have a bunch of imaginary values. Okay. And I don't know, you want to normalize those or whatever, computing some absolute value. The problem is transform, it has 1 or 2 inputs. And that's all. So what if you want to have something a bit more meaningful? Well, you can use a zip view that will take both of your vectors, of your ranges, and turn it into a single ranges where every time you iterate over, you will get a tuple of 2 elements. Okay. So this will be a transform 2, because we are going to replace the real part of the scalar by its absolute value, by its modulus. Okay. So the input will be a zip view between the 2 things. Okay. So it's Eve. It's Eve what? What it is actually? Let's check. Do we have the documentation for zip? Zip range? Yeah. View zip. Okay. Do we have it? Okay, fine. Okay, view zip. Okay. Okay, let's have a look at what's going on now. How is it? No, it's probably there. Sorry. So let's have a look at zip. This one. Okay, it's views. Okay, views. So you can do views, and you can zip an arbitrary number of arrays, so really max there, and I'm going to put my output into it. Now, what does this do? Now we are going to walk over the data in lockstep. So every time we load a piece of data from the zip, we load a vector from real and the corresponding vector from image. What the thing we got there, it's not one value anymore. It's basically some kind of tuples. Okay. And so what we can do there is we can do the following. We can destructure it to get back R and I from this. Okay. And then we can do some computation from that. So I don't know, something like that. And we return a single value. Done. What does it look? And then we are going to make it run to see what's going on. Where is it? Process algo is down there. So we have a bunch of some more. Oh, let's remove that too. We have some more epilogues to handle the zip, but it's a couple of pointer chasing code anyway, so that's not a big deal. Let's have a look. Where are you? Where are you? Where are you? Oh, probably so. Is it there? Yes. Yes, it is. So if we look at what's going on into the main loop, which is probably around there. Yep. So we see that we load multiple values in two different registers. We do the computation and the stores, and we continually do that. So we just zip the values, pass it as a zip iterator to the operation. This zip thing is loaded as a tuple of y, and this tuple of y is destructed into this. So we can actually do that. We can actually pass zips of ranges, okay? And so you can sort of do, structure of array computation with that. We also have a structure of array vector class that lets you do that without having to do the zip yourself. So you can pass a vector of something, and if the something is a struct that we recognize as such, it automatically gets spliced this way. But then we can do this. So, fine. So we can have transform-like loops. We can do funky things like zips. And we have a different way to handle the computation. Inside the lambda we pass to the algorithm, it's basically normal len. Okay, we just do some operation on the y. Now, let's do something. Which is the following one, just so we understand how the thing is going. So let's say we have R, which is like, I don't know, some amount of value. I don't know how much. This is I. So let's do something real quick by doing this. Yep. And so what I want to do now is basically call process sim the algo of Ri. Okay. And what I will do is do something there. I will put some print over there to see what we have. So what's E? And we can count how many times we go through that. And what's R and I? Now what about doing this also? Well, the result we don't really care, sort of. Let's execute the code. Let's look at the output. Okay. So how many elements do we have? Probably enough to at least have two results. So let's have a look at the result, actually. Let's unzoom a bit. Okay, let's not unzoom a bit, but let's have less things per, register. Let's go to this. Okay. Okay, so, oh yeah. Okay, so if you look at what we have there, it's not actually a tuple. I lied. It's not a tuple of y. Because if it was a tuple of y, either it won't have been printed if it was a std tuple, but it's not, or we would have had something like 1569 and then 21546. If you look at what we have 1, 2, 5, 15, 6, 4, 9, 6, which is basically the zip interpretation of what we have. Wide doesn't actually just work for regular types. You can pass tuple to it, and when you have a wide of tuple, it's stored internally for you as a tuple of wide. But every time you apply a function on it, it just unzip it before doing the things. So basically, a wide of tuple is a small-scale SOA system. So there we build a tuple of float-float, and we have a wide of tuple of float-float. That's why we have that. So we see that we have every pairs inside. And when we do the deconstruction using auto brackets, we see that then we got 1569 and 21546. But this costs us nothing. This is all automatic. I mean, what is costly there is actually printing E, because we have to do the dance. But everything there is stored efficiently as 2 whites. Okay. And so if we look at this, we see that we go over all the data. Okay. Now, I didn't do it on purpose, but it fit exactly. So I need to add one more data there and there. So we probably shift the value by a bit. Are we? We did? Yeah, we did. And look at this. So the last value is what? Is 6x. Okay, that's the last value we read from the array. And basically what we saw is that the way the address is computed, the way it moves, and the way the compiler wrote the things, we see that basically the remaining data we added just shifted everything by 1, and we end up with the last value, which is full of garbage at the end. And if you look at what you do there, we didn't clean it up before. We're just giving you garbage anyway, and that's the store of the results that is going to do the correct things. So this is one thing that changed from maybe what you have the habit to do, is that whenever we do an operation inside the transform or any other algorithm, you may encounter computation done on the wide with some amount of garbage. And this garbage, we don't know what it is. Maybe it's a value that is okay to pass to your function, or maybe it could not be. Let's say we do square root and we have a negative garbage. We end up with a none or something. But that also means that we cannot, that's a big limitation, we cannot enforce precondition of function inside an algorithm because we know that we need to work on garbage. Because at the end, we know that we never store garbage. Okay, so that's one thing that is a bit different than you. But we see that we don't have any places where we call the operation on the scalar. Everything is fully vectorized. And we have this nice bonus of having a way to handle wide of structs or tuples. Okay. So you can actually do work on structs. There is a tutorial in the doc about that. I'm not going to speak about it today, but you can actually build a struct. There is a small thing you put on it to adapt it. And once it's adapted, we know it's a struct, and we are going to have wide of these things without any issue. So if I go back to AVX2 now, so AVX2 has a more bigger constraint on alignment. It's aligned on 32 instead of 16. So maybe we should have some, yeah. Now we see that we have garbage before, for example, and we probably have garbage at the end, but less, okay? But it's not a big deal for us. We are not going to do anything with it, okay? So why is it interesting to speak about that? Why is zip something that may be interesting for what we want to do? Okay, in the middle of the Rescott formula, we have these stencil things going on. Okay, there is something I wish to do, but I never have time to do it, but maybe next year, I don't know. I shouldn't say that because Pierre is in the room, so he will tell me you said that last year. What we should have is to have some kind of stencil transform. You give it your stencil somehow, and it do everything for you. Okay, but it's a bit more complicated than that. So currently, what we can do as a stopgap measure, actually, so for those people that follow using the Docker, you can have a look at the stencil.cpp file that I will put into the things. So we can have a look at is what do we want to do actually? If I have a stencil, right? Okay, let's just me do something. So let's save that. Before I forgot to save it. Okay. So what happens when you do a stencil? Okay, let's do a simple 1D stencil first. Because 2D is just the same but more complex. You have your data, right? You have a bunch of data. And what you want to do is you want to load some of them and do a computation to get a result for the center of the stencil. And you want to move this window across all the data, right? So you want to compute, let's say, that. And then you want to load that to compute this result, okay? And so on, and so forth. If your stencil is trivial enough, like it's a complete stencil, it's based on float or double, there is no complicated memory pattern, most of the time, maybe some autovectorizer will autovectorize. So our goal as Eve developers, we know that they have got autovectorized in the simple cases. What we wish we could have in a steady way is that could I get a speed up of slightly above 1? Okay, maybe 1.5 or maybe 2, but we know that we are not going to win a bunch if we do it this way. 2D stencil is very different depending on compiler. And as soon as you have something which is not compact or which is very complicated in terms of the stencil shape, most autovectorizers say screw it. Okay, and that's where we came in. So what do we want to do? We want to do this, but the scalar version is trivial. You just move around, okay? Oh, wait, exactly what I wanted to do. Yeah, in fact, yes, it is. So the scalar version is something like this. This is a 1D thing. So I have an input and an output. I'm using span there, so I don't have to deal with vector or whatever. You can pass what you want. You are going to walk down the data and you load with this stencil pattern, okay? What would you do? Question, open question also in the online room. What would you do if you want to vectorize that? And let's have a look at this drawing. And what do you think should we do? Where are we going to load the data by pack of whatever? What are we going to do? Okay, I remember, let's put back the original one. We load that, we do some plus, for example, and we get a result that we store at the centerpiece of the output. Now, this is a trick question, because you see we are going a stencil of 3. And we could say, I mean, I have a vector of 4 floats. And Matt told me that 3 is smaller than 4. Okay, maybe what should I do? I should load my 3 things in my register of 4 values and do some shenanigan inside, and I get my results, and I do the same next to it. But if we do this, we are not doing vectorization because we use 1 vector of 4 values to compute 1 result. What we want to do is we want to load some amount of register of 4 values to get 4 results. So one thing you can do, because sometimes you don't really know what to do. It's complicated. The algorithm is not easy to read. Take your algorithms. Let's take this scalar algorithm, actually. And I'm not going to change the loop, but in your head, you can say, yeah, I have 4 outputs to compute. So I should do something like this in the end. Okay, and whatever. And if I compute that, what do I have to read from this? Oh, that's 4 times I everywhere. Yeah, that's the time you have to invest into a text editor with vertical edition. That's the best you can do when you do vectorization code. Plus that. Okay. Yeah, God, I love this vertical edition. So that's what's going to happen. Yes, I forgot something?
Yeah, you did plus.
What?
The second one is 4 plus I instead of 4 times I.
Oh, yes. Sorry, I didn't see it. Yeah, of course. Yeah, thank you. So by doing the correct computation, why is it helpful actually? Well, now, look, we know that if we have something on the shape, some origin plus 0, 1, 2, 3, that's a 1, because we are loading contiguous bit of data into a single register. Okay, so 4 times I is my origin value. So let's do this. Let's move everything this way. Oh, I did something bad. Whatever. Okay, so yeah, you have to invest into something that lets you edit stuff vertically, and you have to learn how to do it properly. That's I apparently forgot to do the second part. That's not a big deal. Yeah, completely. So we got that. So now this is a wide. This is the output wide, actually. Exactly, because it's 4 value one after the other in memory. So that fits nicely in a wide, because when I will store that, I will get my result. Now, there is another wide I can see from there. This is the middle one, because it's also O plus 0 plus 1 plus 2 plus 3. So somewhere we have WI, which is the perfect central thing. Okay? Okay? The time scale doesn't change because that's scalar code. Okay, that's where we are going to. And what are the other ones? Well, this one is basically a wide also, because it's plus 0 plus 1 plus 2 plus 3, but one value before. So that's basically exactly WI, except I loaded it from one value before. And the other one is the same one, but loaded one value after. So actually, we can do this. We can say that WI is loading from this. That's the middle part. And we have the other one. So let's call it M and P for minus and plus. Okay, we do that. Okay. But we don't give a crap about the 4 times, because the 4 times was there because we wanted to do the unrolling. In fact, okay, let's do it properly. That's exactly what we want to do. And we are going to store into out of I. And so as soon as we do that, we can actually go up there and see what's going on. We are going to load that into the WM. Okay. Okay, we start from this one, obviously, so we can have something behind. The middle one is this one. It's the same thing, but stranded by 1. And the plus 1 is this one. So we load full wides, 3 full wides. Exactly the same number of wides as we have elements in the stencil. And that's rather trivial, actually, because it's exactly the same code, except, let's go back to the regular things. Now, that was the that's the original code, right? Wherever we load in at I of some in of something, we are going to load the wide at exactly this place. And now, what happens when I do the next step? The next step, move every addresses by 4. Okay, so, well, fine. I'm going to load that now. I'm going to load that now. And so on and so forth. I'm just moving my stencil of 4 things at a time. How many results do I compute? When I do this addition, multiplication, whatever on white, I have 4 outputs for my, my computation. So I consume whites and I output whites. Okay, I'm vectorizing. Okay, the trick there is not to think that because you have 3 or 7 or some number like that that fit into a single wide, that's the correct solution. Every time you touch one scalar point, it has to become a wide from the place it is. Okay. So now we can actually have a look at the actual vectorized things, because now we have 3 things to work with. The middle one and the 2 other ones. So if we want to transform a piece of data with that, we need to pass it these 3 inputs. Oh, well, that's cool because that's a work for zip. So one very crude way to write a slide stencil thing is to say, okay, this is my input. I'm computing some span of sliding things, okay? So I'm doing 0, 1, 2 instead of minus 1, 1, 0, 1, but that's the same thing. They start slightly shifted, 1 element less, okay? And I transform to the output what? Well, the zip between the first one, the middle one, the other one. I destructor them inside, and I do the stencil. Fine. Looks cool. I mean, we have a transform, we have a zip. We didn't even have to bother about computing how many times I need to whatever. I can decide to enroll by how much I want. Okay. Let's have a look at the code that this thing generates. And then on my machine, we are going to have a look at the performances. So that's also important. So that's the scalar version that I suspect the compiler should be able to auto-vectorize. Right? Let's have a look at the loop. And yeah, it does. And something says that we are on the good track. Oops, sorry. Because if we look at the things, we have add a mul, and we have 1, 2, 3 loads with slightly different pieces of addresses. Okay? So it probably do exactly what we do. And then it does the same thing because it enrolled, blah, 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 and then the final scalar thing. Okay, what do we do? Okay, wait, is there? Okay, we do the same kind of main things there. We have a first loop there. 1, 2, 3, 4. So we enroll by 4. Okay, and then we have the final ending of the thing. What if I say that I don't give a crap about enrolling? Yeah, we got something similar, except we don't do the enroll. Yeah, so we got that. Okay, now let's have a look at this. Did I already compile them or not? Yeah, let's have a look at stencil this way. I don't know which version I have. So it's H2. Okay, it's a small array. Okay, we have a speed up of 1.24. We could say, meh, that's meh, because we should go 4 times faster than the scalar code. No, because we know the scalar code is already vectorized. So actually, it's not a bad win because we are 25% faster than the auto-vectorizer. Now, you could have a look at stencil 2, which is the exact same version, except now we do something in 2D. So in 2D, we have 9 points. So let's do the crudest thing we could do. So we have a matrix to storing the 2D data, but it's not very important. That's the scalar code, okay, right? And we're just going to slice the things 9 ways, and then we have a loop over call to transform that basically let me enroll the 9 points and do the computation. I'm going to go back to that a bit later. So let's see what stencil do does. Is it good? Yeah. Sort of there. Okay. Sort of. What we are missing is the following thing. Look at how I do the computation there. I got my 9 things. Okay. And I do some, I do stuff by columns, and then I do the computation there. If your stencil has some properties, if it's separable, actually what we could do, and I think it's not the case with the Gray-Scott reaction, you could actually turn your 3x3 stencil into 2 1x3 stencil, 1 horizontal and 1 vertical. And what you could do is compute the vertical computation and do the horizontal with the result. But what you do is instead of reloading everything, you just load the last column because you know that the intermediate result for the next step, you already have them. So this C2 will be end up in C0, C1 into C0, C2 into C1, and you just have to load the data for computing the new C2. And that's basically turn your n square stencil into something akin to 2 times n operation. But we cannot do this with transform to n zip because we don't have the space to do it. So we should need to do that by n at some point. Okay, now, last thing I just want to tell you, because it's probably the end, just show you that. We also are working on another tools, which is above Eve, which is supposed to solve some of these problems. Where are you? Where are you? Is it you? Yes, this is you. Yeah. So it's called Kiwaku. It's another library that deals with arrays, okay? And basically, we only deal with arrays. We don't do any computation. You have to do the computation. But it lets you write stuff like this. So where is the actual stencil? Yeah, here it is. you can take data, okay, that you can take view over, okay, with these things. And we have algorithm, a bit like we have in Eve, that works on your real array. And in this case, what we do, we can also pass tiles. Okay? So what we do is that we pass 3 by 3 tiles to the for each. So every iteration of this is basically getting a tile, computing where you should be in the tile, and calling another for each that will do the your stencil things over the tile. Okay, and the tiles are themselves compatible with Eve, so you can actually load data from the tile and do vector operation inside. So Kiwaku basically provides view and table-like objects that lets you deal with all the view, tiling, whatever things, okay? And then you can just get the data, and the data you can decide to process them the way you want, okay? Okay, so thanks for everything. One last thing, one last note. So you can, again, as I say, you can get the slide back there, okay, if you want to have them. I will upload some of the examples over there during the week, so you can actually have them. Last year, at CodeRecons, we sponsored the Grace Pool by providing some free subscription for our online training things. This year, we are doing something different because you are more on that. There is some kind of promo code if you want to subscribe, so I will let it there. So up to the end of the summer, if you subscribe with this, you can get a discount. Don't hesitate to ping me on the chat or later if you want to get more information. But we provide training around the subject that was probably the subject of last week and this week, and we have a bunch of other offers. So yeah, if you want to get a look, you can get something like that. Thanks for everybody. I will be available on the chat the whole week. I will be available up to Thursday there. So if you want to catch me up, discuss something over your algorithm, why you think it doesn't work, why you want to test it, or if you want to test even more complex situation, don't hesitate. I will be very glad to give you some information. So thank you. Have a good lunch and see you next year.
What is this subscription about?
What?
What is this subscription about?
Yeah, we have. I forgot to speak about that. We have some online training systems that we provide on HPC and whatever. We have regular online training, okay, like face-to-face things, and we also have some kind of self-paced learning systems. So this is for subscribing to the self-paced subscription. So you have access to a bunch of online courses on different subjects. You can have a look later if you want. So this is something that is renewable annually, and you get access to a rolling subset of courses. Every course is automatically self-assessed by our exercise systems, and you have also some support from the teacher and whatnot. Okay.
You have one on compiler?
Sorry?
You have one on compiler?
Sorry, I didn't catch it.
Compiler.
On compiler, not in the self-fast one. We have an actual training about like what should you expect from the compilers and how to tail it. But it's not in the self-paced one because it's more we need to know interaction for that. Yeah. But we do have something like that. Okay, thank you.